Hello, I am Son, a master student at Lab 성균관 University. I would like to introduce our paper, Disrupting Diffusion-based Inpainters with Semantic Digression. Before introducing the paper, I'd like to first introduce our lab. Our lab name DASH stands for Data-Driven AI Security ACI, which is simply dealing with AI security issues. Our lab consists of 10 PhD and 19 MS students, and we publish numerous papers in top-tier conferences every year with our advisor, Professor Simon Wu. Our lab's research interests are as follows. Along with cutting-edge research like the diffusion disruption that will be introduced now, we are continuously conducting research on time series anomaly detection, defect detection, and more. If you are interested, please feel free to contact us. Our paper has been accepted on IJICAI 2024. IJICAI covers a wide range of AI topics, from classical algorithmic problems to LLM, VLM, and trustworthy and ethics. This year, around 700 papers were presented with an acceptance rate of approximately 10%. The conference ranks 9th in the artificial intelligence area on Google Scholar and has a BK21 score of 4, making it one of the tougher conferences in the field. So I will now begin introducing our paper. Recently, deepfakes have emerged as a serious social issue. Deepfakes can be created by maliciously using generative models, with inpainting and editing being methods that more easily violate personal information. Here, we aim to suppress deepfake generation, focusing on inpainting. Below is how inpainting works. As shown in the image, we can use a generative model to fill the unmasked white areas with desired prompts. In this example, by inverting the mask and providing an appropriate prompt, we could create a deepfake that preserves the dog's identity while generating a new background. In this paper, we aim to proactively defend against the generation of deepfakes through inpainting techniques. To achieve this, we need to apply special processing to images containing our personal information before they are distributed on the internet. We know this is an adversarial attack, and in this research domain, it's also called image immunization. This can be applied to inpainting as well, as shown in the image below. Here, inpainting models referencing our adversarial noise fail to properly express the prompt. For example, we can see that the teddy bear is not in front of the Tower of Pisa as it should be. The previous work, PhotoGuard, also attempted to disrupt inpainting. As you can see, PhotoGuard optimizes adversarial noise by allowing the input image to follow the entire diffusion process, then using loss against the target image at the end. However, there are several limitations due to the method structure. First, it requires a large amount of VRAM to store and optimize gradients occurring throughout the diffusion process. Next, the optimization process takes a long time as a result. Finally, the target image is suboptimal. PhotoGuard's targeted attack varies greatly in performance and difficulty depending on the chosen target, and often fails to disrupt the inpainting model's generation. Our work aimed to address the vulnerabilities of PhotoGuard and achieve more efficient and effective disruption. In brief, we resolved this by using an untargeted attack with multimodal targets. An untargeted attack is designed to make the predicted value deviate from the input data, moving the inferred value away from the previously obtained result. As we refer to the previously obtained value as the target, it has to be designed considering the input of the multimodal inpainting model. In our work, we first find the target as the value h generated from the self-attention layer of the inpainting model from the input. This is because the h contains richer structure and meaning of the image, making it effective to disrupt. If we call the space forming h for the input latent as h space, our attack method maximizes L hidden in the equation on the slide. This means that the source extracted from the input value moves away from the target. In this figure, we can see that h is extracted from the results of several layers in the middle of the Stable Diffusion unit. Next, we addressed the VRAM and optimization time issues of ForGuard by attacking the vulnerable time step we identified. As you can see in the red box, we found that the vulnerable time step was around 720 in the diffusion process between time step 0 to 1000. The early time steps of the diffusion process form the overall spatial structure and general meaning of the image. Notably, the characteristics of h around time steps 720 shows the most similarity to h at other time steps as mentioned earlier. This figure is introduced in the supplementary section of the paper. It shows the cosine similarity between the eigenfeature of h obtained from all time steps and h at different time steps. As you can see, the cosine similarity is highest around time steps 720. These images demonstrate the results of attacking and then inpainting using various time steps as vulnerable time steps. The higher the cosine similarity, the better the attack performance. These results reveal that there is a vulnerability in the diffusion process that varies depending on the time step. Next, we'll address the issue of target setting. Since we are leveraging an untargeted attack, we need to focus on forming a target that moves away from the current state. In this paper, we perform attacks on the h space, so the target is basically created through h. As the inpainting model is also a type of generative model, we need to consider images that vary depending on the seed. Therefore, we should use the expected value of h's obtained from the multiple latents sampled randomly, in other words, Monte Carlo sampling, as our target. In the equation below, Z large T is the initial latent of the diffusion process, C is the masked image, tau is the text embedding, and T is the vulnerable time step. Among these various input values, I'll introduce the process of finding targets for C and tau, which are the variables we can currently optimize. Based on our previous work, we were able to create targets in H space. However, we found that the ambiguity of text embeddings in high-dimensional H space negatively affects target formation. Therefore, we propose a multimodal target created by tuning the prompt as shown in the red box. As the prompt is tuned to better represent the context image, H moves along the red arrow in the right figure, which helps inpaint images that are more coherent with the context image. Once prompt tuning is complete, we can obtain a more calibrated target through the tuned prompt, resulting in better performance. As we explained earlier, we needed to find the text embedding that represents the context image. First, we could directly obtain the text embedding through the loss function of the diffusion model. For reference, the text embedding is created by passing prompt tokens through a text encoder so that the generative model can understand the prompt. However, at this stage, we are generating and optimizing a new text embedding, so we initialized the text embedding randomly. At this point, we can optimize using the following equation for the mask M. The inverted mask is used to fill in the context image rather than the background. However, while this approach is the simplest, it tends to overfit in an unstable manner. The current slide uses the same objective function as the previous slide, but introduces the process of optimizing in token space. In this equation, pi represents token embedding, which is converted by nearby existing tokens through a project function. It then passes through a text encoder before being input into the model. The only difference from the previous equation is the addition of the project function and encoding process. This discretely projected optimization keeps the prompt more realistic and better describes the context image while staying within token space. In the illustration, as the initialized pi is optimized, it better expresses the original context of tiger, and the word tiger actually appears in the prompt. In conclusion, we can obtain multimodal targets through optimized token embeddings and apply untargeted attacks using the given equation. As shown by the blue arrow in this figure, we can immunize the context image by maximizing the L2 norm. Our method primarily uses PGD. Since the inpainting model is a generative model, we perform one PGD optimization step using the average gradient change obtained by multiple random seeds. This framework we've discussed is our proposed DDD, which is digressive guidance for disrupting diffusion-based inpainters. Now I will introduce our experiment on DDD. Our experiments were conducted using an 140 GB GPU. For foreguard and our method, we used an epsilon of 12/255. We also used 7 PGD gradient samplings for gradient averaging. Finally, we performed 250 iterations for optimization. Now, these results qualitatively compare our method with PhotoGuard. After immunizing with DDD and PhotoGuard, inpainting with the prompt on the left shows that PhotoGuard only creates minor artifacts, while our method prevents the prompt from being properly expressed. The tiger example at the bottom was one of the most challenging to immunize, but we were able to achieve visual disruption through multimodal targeting. We evaluated performance quantitatively using 381 image prompt pairs and various impeding strengths. This experiment is more comprehensive in quality and quantity compared to the one introduced in PhotoGuard. Through this experiment, we demonstrated better disruption performance than PhotoGuard in all results, including clip score and aesthetic score. These results show that our method achieves proper semantic disruption. The remaining metrics indicate the degree of visual disparity with Oracle inpainting, which also showed superiority over PhotoGuard. Additionally, in this table, R represents Stable Diffusion version 1.4 and S represents version 2.0. The arrows indicate where the model was immunized and what it was impinted with. For example, R to S means it was immunized on R and impinted on S. This table also demonstrates that DDD outperforms PhotoGuard in transferability scenarios. Upon closer inspection, DDD's transfer scenarios often perform similarly or better than PhotoGuard's non-transfer scenarios. These results indicate that DDD exhibits transferability across various versions of Stable Diffusion. We were also able to directly show transferability as follows. The images in the green boxes are impinted from non-immunized images, while those in the orange boxes are impinted from images immunized with DDD. As you can see, our method results in creating disrupted images contrary to natural inpaint. Next is human evaluation. As disruption may not be adequately assessed through quantitative or qualitative experiments, we conducted a human evaluation. We provided 31 survey participants with 20 images each. For each question, we asked them to choose between DDD's result and PhotoGuard's result, based on which was semantically and visually better. As a result, PhotoGuard received over 90% of the votes in each question, supporting the strong disruption performance of our method. Our evaluation study demonstrates the validity of token embedding optimization. This figure shows various targeted and untargeted attack scenarios. SNT represents source and target, respectively. When the source moves closer to the target, is a targeted attack, while the source moving away from the target is an untargeted attack. We experimented with various sources and targets in each scenario and found that untargeted attacks, especially when the text embeddings of source and target are the same, yielded significant results. In D and E, we can see the difference between using optimized token embeddings and not using them. A more rigorous quantitative comparison is addressed in the table on the right. Here, DDDA represents the case without token embedding optimization. Through most scores, we were able to demonstrate the necessity of token embedding optimization. Finally, we conducted experiments on the robustness of DDD. The inpainting model operates based on stable diffusions, image-to-image pipeline, where higher inpaint strength results in better defect quality. As shown in figure on the left, we show that DDD performs well across various inpaint strengths. Additionally, the figure on the right demonstrates robustness to augmentation. We were able to verify robustness using the augmentation setting below, but we felt that there was still room for improvement with larger augmentations. Well, we'll conclude our introduction to DDD here. The first thing we realized while working on this project is that inpainting disruption is an emerging task, and a major issue is the lack of absolute metrics to evaluate disrupting performance. Additionally, both DDD and PhotoGuard are vulnerable to augmentation and mask positioning. We hope these points will be improved through future work. In conclusion, we identified vulnerable time steps in the diffusion process and performed untargeted attacks using multimodal targets through token embedding optimization. This improved both VRAM usage and optimization speed for attacks by 3 times, and we demonstrated better disruption performance through various experiments. You can access our project code and paper through these QR codes. More qualitative results are available in the paper. Thank you for your interest in our research.